I'm going to have a circuit. Given this following circuit, the way I'm going to change it is on the one that he had is they're both D flip-flops. I'm going to make one of them a T flip-flop. Given the circuit below, let little y1 and little y0 be the present state variables. And capital Y1, capital Y0 be the next state variables. Analyze the circuit below. To derive the next state expressions. The output expression. And construct the corresponding state assigned table. We're probably going to do a state diagram too. Now, if this, I said this was from Dr. Trahan, Professor Vady would also ask you to give the excitation equations. So I'll just add this in here. And we'll go ahead and do the state diagram too. So this will get everything in there. Okay, so here is our circuit. I have 2 AND gates. I'll have one input here, lowercase a. I'm going to have a D flip-flop here, and I'll have a T flip-flop here. And this input will be little y1. This input will be little y0. So that means this output is capital Y1, and this output is capital Y0. And we have this. It's Q bar, Q bar, and oh, you know what? I actually have this backwards. These are this is actually the present state right here, and this is actually the next state. I know it seems weird, like it doesn't seem like that's what it is, but these should be the capital letters and those should be the lowercase. Yeah, these need to be lowercase over here. And I had that and that. Okay. And I have my output here, G. Okay, so first of all, this is a Moore type machine because it does not depend directly on the input. If I look at my output right here, G, see how it is depending only on the state. It's only depending on these variables right here directly. Of course, at some point along the line, A was important in determining what it was, but A is not a direct input into G. So this is a Moore type machine. Okay, so in order to get this going, we have to know the characteristic equations for our two types of flip-flops. So our characteristic equation for a D flip-flop is very easy. So for D, the output is the same as the input. But for a T, we have a different characteristic equation. And let me get that for you. There we go. Let me write all of them for you. I think these will be handy for you to have if you have one of these equations. So these are the characteristic equations for the different kinds of flip-flops. So for an SR flip-flop, Q star equals S plus R prime Q. For JK flip-flop, Q star equals J Q prime K plus K prime Q. For a T flip-flop, I think I need another input for my T flip-flop, so hold on. T flip-flop, no I don't. For T flip-flop, Q star equals T exclusive OR Q. And for my D flip-flop, Q star equals D. So those are important. So now I'm going to write my excitation equations. So D equals just the AND of Y1 and not Y0. And T equals the AND of A and not Y0. Did I get that right? No. Yes, that's right. Okay, so those are my excitation equations, but to get my next state equations or my transition equations, I have to also use this right here. I have to use those. So this tells me that my top one was Y1. Y1 is D, and D is the same as, Q star is the same as D, so Y1 is just going to be little y1, y not Y0. But T, its excitation equation is T exclusive OR Q, and that's what Y0 is going to equal. Well, T is A and Y not Y0 exclusive OR Q, well, Q is the output, and the output for this one is Y0. So this is my excitation equation, this is my transition equation for Y0. So that's Y0 and Y1. Okay, now what I want to do from there is I will want to do a Carnot map. Do I need to do a Carnot?
Is that capital Y1 equal to lowercase y1 Y0 at points? Is that the excitation equation too? Or is that the transition?
These are the transition equations, sorry.
So why didn't for the T flip-flop,
Yes.
what happened to the last half of the equation? Why didn't we have anything for Q?
I do. Q is Y0. Does that answer your question? Yeah. So this is T from right here, and this is Q right there. Yes.
What exactly is an excitation?
I'm glad you asked, because when I first started doing this, I was like, I don't know what this is. So the excitation equation, what it is you're looking at what is the input into the flip-flop. So I'm looking at the input into the flip-flop, and like for this first one, for this D, it's an AND gate. What's the AND of what? The AND of Y1 and not Y0. So this is excitation equation 1, this is excitation equation 2. It's the inputs into the flip-flops. And then the transition equations, or next state equations, are you take those and you apply them to the characteristic equation of that flip-flop. Okay, so let's do I don't think I actually need to do a Carnot map here. I think we can do this without it. So let's do our state table. So we've got present state will be Y0. What order do I want to do this in? I want to do Y0. There's not a rule on this, by the way, and the two professors do them in different orders. Y0, Y1. Y0, Y1. And my next state will be capital Y0, capital Y1, and capital Y0, capital Y1. And the reason I have two of them is because it depends on whether A equals 0 or A equals 1. And I have my output, and my output, because we determined that this was a Moore machine, I don't worry about what my input is. I just have one for each state. Now, I only have 2 flip-flops. That means I have 2 to the 2, or 4 possible states. And I think so we have that Y0. Let's start with Y1 because Y1 is easier. So Y1 is Y1 times the naught, and the naught of Y0. And so it doesn't, notice there's no A in here, so whatever I get for Y1 is going to be the same in both of these columns. So since this is an and, if y1 is 0, the and of 0 with anything is 0. So I'll have a 0 here and a 0 here. This column is going to be the same, 0, 0. And then when y1 is 1 and y0 is 0, then I will get, so the only time this is going to equal 1 is when y1 is 1 and y0 is 0, and that's right here. And otherwise it would equal 0. Okay, so now let's look at y0. That one is a little harder to see, so I'll make a truth table for that. So I've got my two variables are a and y0. So I've got a and y0. And then I also have a y0 not, and then I have a y0 exclusive or a y0 not. So 4 possibilities. And then I'll fill this in. Okay, and you need to remember how an exclusive OR works. Oh wait, I want one more column.
This is all for capital Y0.
Yes. There are different ways of, doing your analyzing. And this, to me, this just seemed like it might be the easiest on this one. So this column is A and Y not. Y not not. So that's 0, 1, 0. Y'all stop me if you see a mistake. And then this is the exclusive OR of AY0 or Y0. Okay. So exclusive OR means one of them is 1 and the other one is 0. That would give us a 1. So that's a 1, 0, 0, 0. All right. Now, this doesn't depend on y1. It only depends on y0 and a. So when a is 0 and y0 is 0, I get a 1. And that's here and here. And everywhere else, I get a 0. So the rest of these will be 0. And then my output was y1 and y0. So my output G was y1 ANDed to y0. Well, that's easy enough to just see right here what it is. So that's going to be 0, 0, 0, 1. Okay, so now we have our state table if I didn't make any mistakes. And now we can do our state diagram. Okay, so let's give these states some names. So it's easier to give them names. So let's call them A, B, C, and D. And then, so A is 0, 0. So everywhere in this state table where I have 0, 0, that's A. B is 0, 1. So that's right here. And C is 1, 0, that's right here, and D is right there. So I can make a state assigned table. So present state next state A equals 0, A equals 1, and output this is A, B, C, D, and this was C, D, A. This was A, B, A, and my output 0, 0, 0, 1. So my states are A, B, C, and D. Now, you'll notice this was a Moore machine, so the output depends only on the state. So I can just write that right on the state. I like to put that it's G, but you can also just put the 0 if you wanted to. If this was a Mealy machine, you'd have to put the output on the arrow, on the transition arrow. Now, coming from each state, you have to have an arrow corresponding to each possible different input. Here we only have a 0 and a 1, but if we had 2 input variables, we would have 4 possibilities. We'd have 0, 0, 0, 1, 1, 0, and 1, 1. So from A to B, from A, if A equals 0, then we go to state C. So this would be, you can write this in several different ways. You can just write A bar or A prime, or you could write A equals 0, and either of those is okay. If he says transition expression, I think he wants you to write it like this. I think this is what he prefers, so we'll just do it that way. Okay, and then if A equals 1, we go back to A.
That is the output.
What?
I was just asking what G was.
Oh, it's the output, yeah. If A equals 1, then it goes back to A. For B, if A equals 0, it goes to D. So that'd be A bar. And if A equals 1, it goes back to B. And for C, no matter what, it goes to A, so I can just write 1 right there. For D, no matter what, it goes to 1, so I can also write a 1 right there. And that is my analysis of the circuit, as well as doing the state diagram.
What's the little representing?
That represents my input, and it's saying, for what inputs do I go there. So let me show you another, since you asked, let's say that I had something, a fancy table like this. Let's say that I had 2 inputs, W0 and W1, and this is just part of a bigger state table. And I have that from A, I go back to A. If I have W0 bar, W1 bar, or W0 bar W1. And I go to B if I have W0 W1 bar or W0 W1. Now this is correct up to a point, but it's not the best answer because this expression can be simplified. If I take W0 bar W1 bar plus W0 bar W1 and I factor out a W0, I'm left with W0 and not W1 or W1. Not W1 or W1 is always 1. So this is just the same as W0 bar. So I can replace that expression with just W0 bar. And I can replace this expression with just W0. So just letting you know that you might have a problem that has two inputs. Okay, I'm going to stop this example and do another example with a sequence detector because I know he wants y'all to know that. So any questions before I stop this one? Yeah.
Go back to that other state diagram with the oranges. So are you using a not as one, let's be one, or is it supposed to be? Because an A, you have like A, like if it's A, then it's going back in, so wouldn't that be 0, or it could be the same? Because it wouldn't change, right?
So this is saying when A equals 1, it goes back to A. A equals 1 is A. So A equals 1 corresponds to A equals 0 corresponds to A bar. Are you sure?
Yeah.
Okay. Other questions?